Hello everyone, I am Bireshwar Roy. I am currently pursuing my 4th year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this NPTEL GATE Physics course, I will be discussing some previous year's GATE Physics questions and try to solve them with proper explanations. This question is from the GATE Physics paper 2020. This is a MCQ type question having 1 mark. The topic of the question is quantum mechanics. The chapter is harmonic oscillator. The question is, let A cap and A cap dagger respectively denote the lowering and raising operators of a one-dimensional simple harmonic oscillator. Let the state n be the energy eigenstate of the simple harmonic oscillator. Given that the state n is also an eigenstate of A cap dagger times A cap dagger times A cap times A cap, the corresponding eigenvalue is option A, n into n minus 1, option B, n into n plus 1, option C, n plus 1 whole square, and the last option, option D, n square. Let us see how to solve this problem. Before going to the solution part of this problem, let us recapitulate briefly about the operator methods used in the harmonic oscillator problem and the properties of the operators. We know the Hamiltonian for the simple harmonic oscillator has the form H cap, that is the Hamiltonian operator, equals to P cap square divided by 2m plus half m omega square x cap square. Here P cap is the momentum operator, m is the particle in the harmonic oscillator potential, omega is the angular frequency of the harmonic oscillator, and x cap is the position operator. Now we know the commutation relation between the position operator x cap and the momentum operator p cap equals to I h cut. Here I is the root over minus 1 and h cut is the reduced Planck's constant. Now we define two special type of operators. Those are A cap dagger and A cap. A cap dagger is defined as root over m omega divided by 2h cut times x cap operator minus I times p cap operator divided by root over 2m omega h cut. And the second operator A cap is defined as root over m omega divided by 2h cut times x cap operator plus I times the p cap operator divided by 2m omega h cut. It is clearly seen that these two operators A cap and A cap dagger are complex conjugate of each other. The A cap dagger operator is known as creation or raising operator, and the operator A cap is known as annihilation or lowering operator. There are some importance or significance of the nomenclatures for these two operators A cap and A cap dagger. When the operator A cap dagger acts on a harmonic oscillator state n, it returns the state n plus 1. Basically, it is raising the state by 1. That is why it is known as creation or raising operator. Similarly, when the operator A cap acts on a harmonic oscillator state n, it returns the state n minus 1. So basically it annihilates or lowers the state by 1. That's why the name of this operator is annihilation or lowering operator. Now we'll evaluate the quantity A cap dagger times A cap. So we'll take the multiplication of these two terms which are coming from the expressions of the A cap dagger and A cap. After multiplication, it will give 4 terms. Those are m omega divided by 2 h cap times x cap square plus I x cap p cap divided by 2 h cap minus I p cap x cap divided by 2 h cap plus p cap square divided by 2 m omega h cap. Now we'll rearrange the terms. So we'll take the first term and the fourth term together, and it will give 1 by h cut omega times p cap square divided by 2m plus half m omega squared x cap square. And we'll take the second and third term together. It will give I by 2 h cut times x cap p cap minus p cap x cap, which will give the commutator bracket of x cap and p cap. Now if we see carefully, the terms in the parentheses are basically giving the Hamiltonian for our harmonic oscillator problem. So we can write it as h cap, that is the Hamiltonian operator, divided by h cut omega plus I by 2 h cut times I h cut. Here I h cut is coming due to the commutation relation between the x cap and p cap operator. So the a cap dagger a cap equals to h cap divided by h cut omega plus I by 2 h cut times I h cut. So from the numerator and denominator, h cut will be cancelled out, and the multiplication of I and I will give -1. So we can write a cap dagger times a cap equals to h cap divided by h cut omega minus half. From here, we'll get an expression for the Hamiltonian operator, that is h cap, equals to a cap dagger times a cap plus half, these terms in the parenthesis, times h cut omega. Now let us see some commutation relations related to the operators a cap dagger, and the Hamiltonian operator h cap. Those are the commutation relation between a cap and a cap dagger operator equals to 1. The commutation relation between the h cap and a cap operators is equal to minus h cut omega a cap operator, and the commutator of the h cap and a cap dagger operator is h cap omega times a cap dagger. Here the a cap dagger a cap is known as number operator n cap, because when this operator a cap dagger a cap or the operator n cap operates on a harmonic oscillator state n, it returns the eigenvalue n, that is the value of the state of the harmonic oscillator. Here the state n is basically nth eigenstate of the harmonic oscillator. Now according to the question, we have to deal with the operator O cap equals to a cap dagger, a cap dagger, a cap, and a cap. And it is also given the state n is the eigenstate of the O cap operator. So we can write O cap operates on the state n equals to some eigenvalue lambda times the state n. So in the question, we have to find the value of lambda. So our O cap operator is a cap dagger, a cap dagger, a cap, and a cap. Now we'll take the second and third operators, those are a cap dagger and a cap together, and using the commutation relation between the a cap and a cap dagger operator, we can write these a cap dagger a cap equals to a cap dagger minus 1. So we have O cap operator equals to a cap dagger times a cap dagger minus 1 times a cap. Now first we will multiply this a cap dagger with the terms in the parenthesis. So we'll get a cap dagger times a cap dagger minus a cap dagger times a cap. Then we can multiply this a cap from the right hand side. So we'll get a cap dagger a cap times a cap dagger a cap minus a cap dagger a cap. So we have taken this a cap dagger a cap in the parenthesis in each case. Now we can identify this a cap dagger a cap is basically our number operator, that is the in cap operator. So we'll write this as in cap times in cap minus in cap. So basically our O cap operator in terms of the number operator is in cap square minus in cap. The operator O cap is acting on the state n. Now O cap operator is in cap square minus in cap operator. So we can write the in cap square operator minus in cap operating on the state n. It will give in cap square operating on the state n minus in cap operating on the state n. Now the eigenvalue for this in cap square operator is n square and the eigenvalue for the operator in cap is n. So we can write it as n square minus n times the state n. So we can see the eigenvalue for the operator O cap is n into n minus 1. According to the solution, we found that when the operator a cap dagger, a cap dagger, a cap is acting on the eigenstate n, it returns the eigenvalue, the option A, that is n into n minus 1. So option A is the correct answer for this question. This question was asked in the GATE Physics paper 2021. There is a numerical answer type question having 1 mark. The topic of the question is atomic physics. Specifically, this question was asked from the chapter Raman Spectroscopy. The question is, the spacing between two consecutive S-branch lines of the rotational Raman spectra of hydrogen gas is 243.2 centimeter inverse. After excitation with a laser of wavelength 514.5 nanometer, the Stokes line appeared at 17,611.4 centimeter inverse for a particular energy level. The wave number rounded off to the nearest integer in centimeter inverse at which Stokes line will appear for the next higher energy level is. Let us see how to solve this problem. First, we will discuss about the rotational energy levels of a rigid diatomic molecule, and then we will discuss how can we get the Raman spectrum from the rotational energy levels of the rigid diatomic molecule. So let us start. First, let us consider this schematic which shows the rigid diatomic molecule, and the atoms in the molecule are separated by the distance r0. The molecule rotates end over end about an axis passing through the center of mass. In such case, the rotational energy levels of the rigid diatomic molecule in quantum mechanics is given by Ej equals to j square by 2y. Here j refers to the total angular momentum of the rigid diatomic molecule. So the eigenenergy of this system will be Ej equals to h cut square times small j plus 1 divided by 2y. Here I is equals to mu r0 square. Mu is the reduced mass of this system, that is m1 m2 by m1 plus m2. So the moment of inertia I equals to m1 m2 divided by m1 plus m2 times r0 square, and the small j is our rotational quantum number for this rigid diatomic molecule. Now, in the case of Raman spectroscopy, we usually represent the Raman spectrum or Raman shift in terms of wave number. So, we will convert this energy of this rigid diatomic molecule in terms of wave number. So, in terms of wave number, the energy of the system small ej equals to capital EJ by hc. Here h is the Planck's constant, c is the speed of light in the vacuum. So, the energy of the rigid diatomic molecule in terms of wave number is equal to h cut square times j into j plus 1 divided by 2I hc with the unit centimeter inverse. Here j can take the values any positive integer including 0. So, the energy levels of the rigid diatomic molecule or rigid rotor in quantum mechanics is given by small ej equals to h by 8 pi square IC times j into j plus 1 with the unit centimeter inverse, that is in the wave number. The rotational energy levels for the rigid diatomic molecule Ej equals to B times J into J plus 1 centimeter inverse. Here B equals to H by 8 pi square IC centimeter inverse. This constant B is known as rotational constant. The selection rule for the rotational quantum number is given by del J equals to either 0 or plus minus 2 only. So, this condition gives the possible allowed transitions in the Raman spectroscopy. For transitions from J to J plus 2 state, that is del J equals to plus 2, we represent it as S-branch line. The excitation energy for S-branch line, that is del J equals to 2 line, equals to del ES, that is given by B into 4J plus 6 centimeter inverse. That can be obtained by putting here J plus 2 in this expression, and then we have to subtract the EJ for J equals to J. So, the difference will give this del ES, that is the excitation energy for the S branch line. Now, if nu Ex bar is the wave number of the exciting radiation on this molecule, then the wave number of the corresponding S branch lines are nu S bar equals to nu Ex bar plus minus del Es centimeter inverse. So, here nu S bar is the wave number for the corresponding S branch line, nu Ex bar is the wave number of the exciting radiation, and del Es corresponds to the wave number for the allowed transition in that S branch line. So, we can write nu S bar equals to nu Ex bar plus minus B times 4J plus 6 in centimeter inverse. Here plus sign refers to the anti-Stokes line. This line comes due to the photon emission by the molecule, and the minus sign refers to the Stokes line. This line comes due to the photon absorbed by the molecule. So, we will discuss this anti-Stokes line and Stokes line in details in the upcoming slides. Let us discuss about the Stokes line and the anti-Stokes line in Raman spectroscopy with the help of schematic diagrams. So, the left schematic diagrams refers to the Stokes transition in Raman spectroscopy. Let us consider two energy levels having the rotational quantum number J and J plus 2. So, the rotational quantum number J will give the lower energy level and rotational quantum number J plus 2 will give the higher energy level. Now, the incident radiation on that diatomic molecule system has the wave number nu Ex bar. So, the molecules at the energy level having quantum rotational quantum number J will be excited to a virtual energy level having the energy nu Ex bar. And then the molecules will release its energy and they will come back to the higher energy level having rotational quantum number J plus 2. So the emitted radiation have the wave number nu Ex bar minus B times 4J plus 6. So if we see carefully, the emitted photon or emitted radiation has the energy less than the energy of the incident photon. So some energy from the incident radiation is getting absorbed in this system. So for the Stokes line, the S branch line to the low wave number side of exciting line. Similarly, for the case of anti-Stokes line, we'll consider the molecules are getting excited by absorbing the incident photon from the higher energy level, that is the energy level having rotational quantum number J plus 2. So the molecules will be excited from this J plus 2 energy level to a virtual level having the energy nu Ex bar. Now, after releasing the energy, the molecules will come back to the ground state, that is the lower energy level having rotational quantum number J. So the emitted radiation or the emitted photon has the energy nu Ex bar plus B times 4J plus 6. So it is clear the emitted radiation has higher energy than the incident photon energy. So for the case of anti-Stokes line, the S branch line to the high wave number side of the exciting line. So this left schematic represents the possible allowed transitions involved in the Stokes and anti-Stokes line. Here we can see the transitions are allowed by the selection rule del G equals to 2. So for the Stokes line, we'll have the transitions either from J equals to 0 to 2 or 1 to 3 or 2 to 4 and so on. And for the anti-Stokes line, we will have the transitions either from 5 to 3 or 4 to 2 and so on. And if we consider the spectrum from this transition, then we'll have the central line which has the same energy as the incident photon, that is nu Ex bar. The first transition that corresponds to the 0 for J equals to 0 will have the separation 6b from the central line on the both sides. So left side's spectral lines will give the Stokes line and the right hand side spectral lines will give the anti-Stokes line. But the transition starts from the J equals to 1 or J equals to 2 for the anti-Stokes line will have the separation 4b. Similar case happens for the Stokes line also. On the left side, you can see for J equals to 1 or J equals to 2, we'll have the separation between the spectral line is 4b. So that is the energy difference between two consecutive spectral line. Now, coming to the solution part of the given question. So we have already seen the wave number difference between two consecutive S branch lines of the rotational Raman spectra is 4b. Now it is given in the question that for the diatomic atom H2 gas, that is the hydrogen gas, 4b equals to 243.2 centimeter inverse. So from this we can calculate the rotational constant for the hydrogen gas system. So for that B equals to 60.8 centimeter inverse. Now it is given that the wavelength of the exciting line, that is lambda Ex, equals to 514.5 nanometer. So we'll convert this in terms of wave number. So the wave number of the exciting line, that is nu Ex bar, equals to 1 by lambda Ex. So that is 1 by 514.5 nanometer. So this will give the wave number of the exciting line nu Ex bar equals to 19,436.4 centimeter inverse. Now it is given in the question that the Stokes line appeared at the wave number nu s bar equals to 17,611.4 centimeter inverse. So therefore we can write nu ex bar minus nu s bar, that is equal to 19,436.4 centimeter inverse, that is for nu ex bar that we have calculated in the previous slide, minus 17,611.4, that is given in the question. So this will give 1,825 centimeter inverse. So if we want to represent this quantity in terms of B, that is the rotational constant of the system, then what we will do, we will divide this quantity by 60.8 and multiply 60.8. So this 60.8 is B for our system. So and this quantity 1825 by 60.8 will give roughly 30. So this quantity is roughly 30 B centimeter inverse. So this gives the shift of Stokes line from the central line or the exciting line nu Ex bar. Now to find the rotational energy levels between those the transition happens with Stokes shift that we have calculated in the previous slide, that is 30 B centimeter inverse. Now from the working formula we have seen nu Ex bar minus nu S bar for the Stokes line equals to B times 4j plus 6. So we will equate this B times 4j plus 6 with 30B. So this will give j equals to 6. So that is the rotational quantum number of the lower state from which the transition is happening. So the transition from energy level 6 to 8 will give the S branch Stokes line with wave number 17,611.4 centimeter inverse, that is given in the question. So the next possible Stokes line, the transition will occur at j equals to 7 to j equals to 9. Now we will calculate the same thing for the transitions from j equals to 7 to j equals to 9. So for that transition, nu Ex bar minus nu S bar equals to B times 4j plus 6 centimeter inverse. So for this transition, j will be 7 here. So we'll put j equals to 7 here. We'll get nu Ex bar minus nu S bar equals to B times 4 into 7 plus 6 centimeter inverse. So that will give 34 times B centimeter inverse. Now B for this hydrogen gas system we have calculated already, that is 60.8 centimeter inverse. So we'll put here, so we'll get nu Ex bar minus nu S bar equals to 34 times 60.8 centimeter inverse, which will give 2067.2 centimeter inverse. So for the transition from j equals to 7 to 9, the wave number of the Stokes line nu S bar equals to nu Ex bar minus this quantity, that is 2067.2 centimeter inverse. We have already calculated the wave number for the exciting radiation, that is 19,436.4. So we'll put it here and we'll get nu S bar equals to 19,436.4 minus 2067.2 centimeter inverse. So this will give the S branch Stokes line, the wave number of the S branch Stokes line equals to 17,369.2 centimeter inverse. So if we just round it off to the integer form, then we will have the nu S bar for this transition equals to 17,369 centimeter inverse. So this is our desired answer for this question. So we solved this problem and we found that the wave number rounded off to the nearest integer in centimeter inverse at which the Stokes line will appear for the next higher energy level is at 17,369 centimeter inverse.